Well, in some ways, you knew this was coming. You knew that we were going to talk about transformations. You knew that every transformation boils down to reflections, and you were wondering to yourselves, when does this happen in the hyperbolic plane? How does this work in the hyperbolic plane? And what happens with those crazy parallel lines that we talked about in the hyperbolic plane? What exactly goes on with that? So I figured that that was worth some demonstration. So consider the following. Bill Nye the Science Guy. So you take some line, like so, and you're in the hyperbolic plane, and so you take some segment like this, and you want to reflect this segment over that line. Well, you can do that. You can reflect this point over that line, and you can reflect this point over that line, and we connect those with a segment, and so we say that segment FH is the image of segment CD. It is over a reflection, after a reflection in line AB. And then we think to ourselves, well, wait a second. I can draw parallel lines. Let's see, let's do parallel to this line. Let's select, oh, no. Let's select this line, right? And let's draw, right? Let's hit the pause button while we figure out what we're doing. Okay, so let's pretend we know what we're doing. So I have two parallel lines, line AB and this line through C, and I'm going to let this be the mirror for E and F. I get myself a segment for an image, because remember, neutrally, the image of a segment must be a segment. And then I take this and play the same game, and magically I don't get any image down here. And that's going to be oh so frustrating, and it's an issue with this particular program. But like it or not, yeah, and I don't like the program. So anyway, if I were to reflect this guy over this line, I end up with somebody down here. And what really ends up happening is that EF just gets translated down to here. That still works even if we're in the hyperbolic plane. The question is, what happens if this is one of my parallel lines and the other line is asymptotically parallel to the first? So CD reflected over AB ended up down here at FH. But now we have a situation we've not had in the Euclidean plane. AB and LM are asymptotically parallel. So if this is the second parallel, F gets, yeah, it gets reflected somewhere over here, but that's not going to work out nicely for us, is it? Oh, I can reflect C. Oh, that's great. I can't reflect reflections. That's a frustrating part of the program. So C reflects over AB, ends up there. F reflects over LM, ends up somewhere over here. One more time, we'll try this again, but no dice. But I could reflect D if I wanted to. If I wanted to, I could make this the mirror and reflect D. Oh, well, let's see. What happens if I try to reflect point S? Oh, I can do it. Okay, so we'll just do it in the opposite order. I'll pick this as the mirror and reflect point C, and then pick this as the mirror and reflect point V. Oh, yeah. So let's recap for all the folks at home. CD reflected over this line and ends up, no. Did I connect them in the wrong order? Oh. Let's get a new one. It's okay. Nobody's actually watching these videos. Got two lines. And they are going to be asymptotically parallel. Take a line segment. We're going to use this as the mirror and reflect D. Going to use this as the mirror and reflect E. I get a segment GK. Then I use this as the mirror and reflect G, and this as the mirror and reflect K, and I end up with MO. When we compose reflections over asymptotically parallel lines, two reflections, MO is the image of DE after a horolation. So now how do we put this in the notes? Well, we're going to take a picture because it lasts longer. I'm going to take a picture of this because you're going to print this out. Oh, no. If you're going to print this out, what we're going to say is that MO is the image of DE after a horolation. And by horolation, we mean a composition of reflections in two asymptotically parallel lines. So if you want, we can think of this as D prime and E prime. This is D double prime and E double prime. A reflection over two asymptotically parallel lines is a horolation. And that's the only new kind of transformation that pops up in the hyperbolic plane. Everything else existed from before. So we can say that every transformation in the hyperbolic plane is either the identity or a reflection or a half turn or a rotation or a translation or a glide reflection or a horolation. And in fact, to get a glide reflection, you have to compose three reflections. And in fact, if you compose three reflections, you get a glide reflection. You'll remember in the Euclidean plane, sometimes three reflections resulted in a glide reflection, and sometimes three reflections resulted in not much of anything. But in this case, three reflections in the hyperbolic plane, three reflections is a glide reflection. And that's what you need to know about the about the hyperbolic plane. So what do you need to know about the hyperbolic plane? It functions just like the Euclidean plane does in terms of compositions of transformations, except that there's this new one, the horolation, that is a composition of reflections in two asymptotically parallel lines. And that's all you need to know about that. Because everything else works neutrally. Okay, so total disaster with the program, but I think you get the point, and that's what I wanted you to get.